gosh, we're live. Okay. No, because if you turn off the light, then the slides can't. Yeah, we can't win this game. You either see the slides or the cursor.
This side.
Uh-huh. Is it okay if I go back and forth because I want to...
Get interest, so it's asked for techniques.
Really?
Mm-hmm.
Oh. You can tell them that you're live streaming, but you go to also
Oh. Do you have a
yeah. Email it to you. It would be nice, in fact, if they post their questions and we can ask it.
very much for Professor Stephen Roberts for hosting us in the Oxford Institute. This is a real honor. Xiaoli Ma will talk about how small are our big data, turning the 2016 surprise into a 2020 vision. Please join me in welcoming Xiaoli Ma.
Thank you very much. I hope I don't need this, right? Loud enough. But, over the years, I've given many talks, and like many speakers, I typically start by saying it's my great pleasure and honor to be here, and sometimes I mean it. And this is one of the occasions that I truly feel honored and privileged to be here for multiple reasons. And obviously, Oxford is one of these institutions that we all admire, but I also really honored to be invited to this group. I understand you have, you're called a PPE, but it's philosophy, policy, and economics, and I don't think you often invite statisticians, am I correct?
Well, yes, we invited you, but most people here are actually part of the Oxford Institute.
Okay.
Most people here are statisticians.
Great, but I wanted to give this talk in a way that trying to reach to as many audience as possible, and I don't think it's sort of obvious why, for example, statistics is very useful for economics, and it's probably also very obvious why it's very useful for policy making. And these days we all talk about what do you call the evidence-driven policies, and probably less so for people to think about the connection between the philosophies and the statistics. But if you really study statistics to a level, you realize many things that we do are fundamentally very philosophical, including the question why it's possible to predict future at all. But what makes it possible? Why something happened tomorrow? We have anything to say today, right? Because we look for patterns, we look for noise, we look for all the all the connections. So my talk today, in a way, is probably not much about philosophy, although I do have another talk. If I do well, invite me back so I can give that more philosophy talk. But I do want to send a pretty strong sort of notion about the importance of paying attention to data quality. As a statistician, many of us don't like the term big data. just because that term emphasizes quantity instead of quality, right? Now, at the same time, we all understand that the data we use in practice probably are never perfect. Never perfect in the sense that they're not perfectly described by these statistical models or probabilistic models that many of you probably have used one time or at another. But many of us probably think about, okay, well, we all understand nothing in life is perfect, but maybe, with so much data, a little bit of deterioration of the quality probably is not that important. Okay, so that's the hope, right? And so what I want to deliver today is really, at least in this particular content, to show you that once you take into account data quality, even it seems like a very small percentage of the deterioration, that actually can really give you a big surprise. And whether you think it's fortunate or unfortunate, there was 2016 election happened in the US, giving many people a surprise, and I'm going to use the data. And I know that you had your own surprise, which I don't have the data, but I'm sure you can relate to in your mind as I'm talking about, to see where other connections are. And so rarely when I give a talk that the papers are already done, but this is one of the cases that actually the paper is going to appear in the next issue of the Annals of Applied Statistics. So you can find the entire preprint on the Annals of Applied Statistics website, and just at the sort of the next issue. That version there has, I just discovered a few days ago, there are still quite a bit of Chinglish in it. I know you understand the phrase Chinglish, right? And so I may still have slightly updated, but otherwise the content is there. And this is what I call a statistical paradise and a paradox in big data 1. The 2 is the more philosophical one that I'm still working on. It's about individualized medicine. How do you think about collect the statistical information in that content? And this thing just gets a little bit more sort of philosophical. So what I want to convey to you today is really to convince you this phenomenon, which I'm calling it law of large populations. I assume, or maybe I shouldn't. Let me do what as a statistician, I should do. Let me collect some data, okay? So how many of you have taken at least one course in statistics? Wow, this is a crowd, okay. So how many of you can claim that you did it very well? Being very modest? Okay. Good. That's why he's the director and you're not. Thank you. Now, seriously, when I usually ask the question, most people would say, I took the course, but I can't claim I did well, or I can't even claim I enjoyed it. And the reason I mentioned that is I will be using these very basic statistical notions. So if you haven't taken the stat course, or if you have forgotten the stat course, that's entirely okay. I'm trying to be very gentle with you today. In terms of the statistical notion I'll be using, I'm actually going to be using really very fundamental notion. There will be no calculus, okay, not even regression in this talk. But what I'm hoping is to deliver to you that how the way of statistician thinks in terms of dealing with these problems that can provide that kind of insight that may surprise you. Okay, so I want to thank my colleagues in a government department. Steve, I can never pronounce his last name, so now I'm going to try. But he's a wonderful colleague. He's that kind of colleague that when I asked him for data, he not only sent me the data, he also sent me his assistant. That's the kind of colleagues you want. And he did Shiro did a really fantastic job in terms. So all the graphs here, everything, really, they were produced by Shiro. Of course, that also means that if there's anything wrong, you know who to blame. So let me tell you, how did I get into this work? Initially, when I started working on this problem, there was a way before 2016, the election. I got into this line of work because I was asked to be. They give me an interesting title, like a statistical data, not data, statistical quality control, right? By the U.S. Census Bureau. So at that time, there's a particular project manager whose name is Jeremy Wu. He invited me to sort of help him to think about certain statistical procedures they were using at the Census Bureau. But he came to Harvard to give the following talk. And during the talk, he raised this fundamental question. This is where I started to work on this problem. Okay? So he said that we know that, he actually went through some historical review, he said we know that a 5% random sample is better than a 5% non-random sample in some measurable ways. Now, since most of you have taken the statistics course, you know when you hear the term random, in a sort of technical sense, it's not just haphazard, anything goes, right? That's not being random, right? The random is, typically what people mean random means that everybody has equal chance. Now, it doesn't have to be that way, but everybody sort of has a known distribution, right? And so for years, or actually for almost a century, that we have convinced everyone that if I want to take a sample, I can take if I do a random sample, let's say everybody have equal probability, then it has the better statistical quality in terms, for example, the estimated sample average will be unbiased, all these quality, compared to some data, 5% that you have no idea. There's a quality rise, okay? But then he asked me, he said, well, but what about this? What about, these days we all talk about big data, and the Census Bureau certainly has all these gigantic data sets, which they cover a large percentage of a population. So he asked the following question. He said, but is an 80% non-random sample better than a 5% random sample in some measurable way? Okay? But now I'm going to pose this question to this audience, especially because you're statistically pretty sophisticated. So I'm going to ask the question. Okay? So suppose you are given the following two data sets. One is we tell you it's a 5% random sample. Let me make it very simple. Let me say it's a simple random sample. Okay? What that means is that everybody had equal chance to be selected. And there's no non-response, that everybody responded when they get selected. And our goal here is to estimate the population average based on that sample. Okay? Now you have these two data sets. One is you have the 5% good quality, let me say perfect quality data, because we know exactly how we did it. There was no complication. The other side is you were given this 80% of population. You were told this 80% population, but that's all you knew. You know. We had no idea how the data was selected. Any bias, we had no idea, but it's just 80% of them. All right? The question then for you is which one you would trust more? Which one, if you're allowed to only use one of the two, which one you're going to use to estimate the population mean in the sense that you would trust more? Okay? So let me see a show of hand. How many of you would like to choose the 5% random good quality paper? Okay, good quality data. Okay? Let's see about. Okay, gradually. Okay, about 10-ish. How many will choose that 80% non-random data? Okay. Don't be shy. There's. Okay.
What is the size of population?
Yeah. See, you give out the punchline of my talk, okay? You're absolutely correct. There's a question about what's the size of the population. But the moment you ask that question, actually, for most people who have not studied statistics, they may find that's a very natural question, right? How large the population is. But for people who actually study statistics, for years we teach people, as long as the population is large enough, you can ignore it. Now, if you think about it, that sounds very ironic. It shouldn't that be that if a population is very large, you should have a hard time to estimate, right? In a minute, I'm going to tell you why historically we make that claim, saying there's something called a finite sample correction, but everybody tells you you ignore that if the population is large enough. Okay. So now I saw that there was about 10-ish voted for the 5%, about 10-ish voted for the 80%. I assume the rest of you still need a cup of coffee. Oh, you're still thinking. But let me change the game a little bit. And this is actually really from Jeremy. He said, now, okay, we still keep the 5%. But what about the other side is 90%? Now, how many of those of you who raised hand for 5%, you will change your opinion now because the other side increased to 90%? Okay? There's one person who will be changing opinion. The rest are probably still holding on to that 5%, which is fine. Let me increase that to 95%. Would you change your mind now? Now I have 95% of my population. Now, it might be terrible data, but hey, I have 95% of them. Would you now trust 95%? Okay, okay. Everybody has a price.
It depends something on the question, too.
Yeah, the question. No, the question here is actually just estimate population mean.
Asymmetric SD population, outliers a big problem, is Gaussian.
I'm sorry?
Does it not depend very much on the distribution?
On the distribution?
Whether
Okay.
it's Gaussian, whether it's dominated by large tails.
Okay. Apparently you have taken more than one course in statistics, I hope. That, well, what about, I further increase again, what about 99%? Somewhere you will say, come on, right? If I have enough data close to 100%, I got to better, right? Would you agree?
Well, if it is a 0-1 response, right, then at a certain point, like it would 99 or 99.9 would probably be good enough, right?
Right.
But
So-
if it is not a 0-1 response, then it can be quite different.
Unless it's an average of something unbounded, because then your
Yeah.
1% could have given some crazy high response.
Okay. Well, this audience is obviously very sophisticated, right? And in fact, that I learned my regression from Professor Obikon. So, and years ago when we both at Harvard. Let me make there is a correct answer to. There is the correct answer to this question. Okay, I will tell you in a minute. But let me make it even harder. Professor Kelton and Tom Lewis, during the joint statistical meeting in 2015, asked the following question. Which one should we trust more? A 1% survey with 60% response rate or a non-published data set covering 80% population? So what makes the question even a little bit more complicated is now, the 80% is still this sort of unknown, but now it said it's a 1% of survey. The complication is with 60% non-response rate. What does it mean that we typically assuming surveys are of great quality, right? In principle, okay? But once you have non-response rate or response rate, what that meant is there's a self-selection process going on, right? People don't respond to you. If they're just flipping coin, not respond to you, you are in a lucky situation because all the reduced is just sample size. And usually what happens is people don't respond to you for a reason, right? And this is actually gets very close to what happened in the 2016 elections. That people refuse to tell you who they're going to vote, right? And for a reason. Now, if the reason is related to the thing you want to know, you can see how the selection bias sort of comes in, right? Okay. So this question essentially is asking us, how do I compare two data sets with different quantity and different quality? That's the research question. Quality, relatively speaking, we all know how to measure it, but it's still only relatively speaking. Then sometimes you have a data set, you don't even know how to measure its quantity, because it's not like everybody has all the observation. You know, some people have some answers, other people they don't, depends on which question you. So even the quantity can be complicated, but usually that's not a big deal. The question then is, how do I measure quality? Right? Measure quality is a much, much harder problem. And you obviously should ask quality for what? For what study you're doing, right? So the correct answer to any of those questions, particularly for all the students, in life, when you cannot answer a question, there's always a correct answer, which is, it depends. The key question then is, it depends on what? Okay? So what I've done in this particular content is I was able to deliver, to derive a quantity which I call data defect index, is trying to quantify the quality, or rather the lack of quality. Okay? And I'm going to show you what that quantity is. But before I do that, I'm going to deliver you an answer in the end that even you see all the mathematics, don't worry too much, it will be a very simple, straightforward one. You will have a hard time to believe these answers. I had a hard time to believe myself, and multiple colleagues of mine say, you better double check everything you have done to make sure there's nothing sort of wrong there. And so I thought about, I'm obviously teasing you that I haven't told you what the answer is. I thought about why people would have a hard time to believe this answer, even the mathematics is so simple. I think that it actually goes back to something that we have overlooked, or we have convinced everyone for too long, and now it's a time to rethink about. What's the question here? Well, think about these election pools. Either in United States or England here, you're talking about a very large country, right? Talk about United States. 330 million people. Even if you just think about the eligible voters population, that's about 230 million people. Now, all these election pools you have seen, I don't think any of us have seen election pool with 100,000 people in it. Have you seen an election pool that large? 100,000 people, like, as a survey.
Oh.
You don't, right? You probably have seen 5,000 people, maybe even 500, right? As these surveys. The question then is, why it's possible? What made it possible that you can learn a 230 million the population by studying such a tiny part, right? Okay? And so what's surprising in a way is that that was possible. And in fact, it was possible to extent that now we teach that all the time. Everybody uses that. We completely take that for granted. Okay? And I want to say, today's lesson, if I can give you one, is that we really shouldn't take that for granted, because that actually is based on an incredibly strong assumption. In order to deliver that, I'm going to take a detour. Right? I'm going to give you a little bit of history, a very quick one, in terms of where this whole concept of sampling come from. And we all know there's this thing called the law of large numbers, right? The law of large numbers simply said, if you have a sort of good sample, you take an average, eventually that average is going to go to the population average you want, right? So that's not that surprising. What's more interesting was this thing probably many of you have also learned. It's called the central limit theorem. Basically, it's studied everything together. You have a bell curve, right? But I think that when people emphasize the central limit theorem, you emphasize the bell curve. For me, there's another message delivered there is actually really, really important. Is it basically said the error rate there, right? The error rate there is 1 over square root of n. N is the sample size. Okay? What is the usual assumption that those things are, being represented in various things? Okay. The whole idea of taking a small sample to study a population goes back to, at least people can search literature from, there are occasionally used back to 1662, and I know these years are not very impressive for this group, but in the US this is pretty impressive. Not impressive to me either from China, but that's a different story. And but it really takes a long time. In fact, this idea that you can study a population by taking a tiny sample was really promoted by Anders, I think it's Kia. Oh, I could be wrong. He's the founder of Statistical Norway, and he proposed that idea during the International Statistical Institute Congress meeting in 1895. Now, you may imagine, now we often take this for granted. This is pretty much the base of quantitative method in social science, so on and so forth. But you imagine that then, this was a revolutionary idea. In fact, it's called intellectually violent revolution. How could it be possible, right? How could it be possible that I can study a population, even say, 200,000 with, say, 500 people? What make that possible? Well, when that's possible, you can look back to see, when you look at this results, you will see there's something missing there. This is only based on the sample size, not the population size, right? Now, we never sort of think it that way. In fact, when we do this simple random sample or those things, we can sometimes even assume the population is infinity. How could it even possible? How could I study an infinite population by looking at anything finite? Right? But these are the mathematical results that sort of leads to this proposal. Now, as you may imagine, that kind of proposal, since it's really intellectually violent, the revolution, it took us a long time. It took a long time for people eventually buy in. This is actually the one statistical paper, this landmark paper by Jesse Neyman, which is the paper many people know has all the concept of confidence intervals, so on and so forth. But that's also the paper where he really talked about these purposive selection versus versus the sort of random sample Y, Y is better, the optimal allocations, all those things. The revolution really lasted about almost like 50 years for people eventually to buy in. And in the United States, that's really because of Morris Hanson, then the director of U.S. Census Bureau. He actually applied that idea in a U.S. census. Now you can see when it gets applied in a census, that suddenly the words get out, right? That this is not just a sort of stamp of approval, but also because the data get released by Census Bureau, people need to use it. They need to understand what this is. So to really take about this sort of 40, 50 years to get this idea really become so we all take for granted. But I still have not explained to you, at least in a very obvious terms. Imagine how you're going to explain this to someone on the street, saying, I have no idea about randomization or anything, but explain to me in a very simple way that why I can study something gigantic by looking at something tiny. And one of the, I have a couple ways to explain it, and this is one of the ways I like to explain it. And since I'm Chinese, I like to eat. And so I'm going to talk about tasting soup, right? Many of you have this experience of tasting soup. You were asked to taste the soup with how salty it is, or how delicious it is, or how terrible it is. Now, you probably never really, when you taste the soup, no matter how large a soup or how small soup, I find a very cute soup online, and there's a very big bucket as well. And what do you do? You never see someone taste a soup by drinking like a large percentage of it, right? Like half of the soup, right? What you do is you mix them well. As long as you mix well, a tiny spoon, or maybe a couple of spoons if it's really delicious, that's all you need. You can pretty much tell the flavor of the soup, right? So what's the key here? The key is this mixing, right? This stirring, okay? And that's pretty much is the reason. It's not a homogeneity, right? If something is entirely homogeneous, are all the same, you don't need to take many of them. You should take a tiny bit, and anyway, it should tell you that big picture, right? And so in general, in life, you can't really take a human population to mix it, and statisticians invent this way called randomization, right? All randomization does is to say, statistically, everyone had equal probability. Now, let me emphasize, it doesn't have to be equal probability. What you need is everybody has known probability. Then you can always adjust. But the principle is the same, right? As long as if I have equal probability, you can see why statistically I can get this thing right. So the theory, central limit theory, all these theories, right? You don't see the population size because it's under this uniform, assumptions built in. Now, so the key work has already been assumed away, right? To get a big bucket uniform is much harder than get the smaller ones, right? But if you assume they have the quality, you have done the work. The assumption has done the key work for you to get rid of the capital N, which is the population size. The little n is the sample size. What I've done in a minute, I'm going to show you mathematically, or rather simple algebra, to show you how the randomizations cancels the effect of the population size, which allows us to do this. What's going on now is when you have a gigantic data set from internet or from self-reported, nobody's doing that mixing, okay? And if people are not self-mixing, there could be something hidden there. And that deterioration is going to come back to haunt you, particularly with large population. But I'm going to show you what I call the law of large populations. The larger the population, the more serious a tiny defect, the more serious trouble a tiny defect is going to cause you. Okay? But this is a fundamental part to understand why later it looks very surprising. The reason is because we have taken for granted so long that we can just do everything by making the assumption that we can mix in anything. All right? So that I want you to keep in mind. Okay. So now, just to tease you, let's see if you are still with me. So where were you on the February 29th this year? No such thing. Okay, you are paying attention. But if you were here on February 28th, there was a talk at Oxford. I was just searching for it. talk about something, the public mathematical lecture here, talk about the Euler formula. Now, why do I talk about Euler formula? Okay, I want to make a connection. I want to give you a formula I want you to remember. And I think probably one of the most beautiful and important formula in mathematics people remembered, even if you don't study mathematics, or particularly if you don't study mathematics, is called the Euler formula. And it's so beautiful, people will tattoo it on their back. Right? So what is the Euler formula? Well, Euler formula somehow connect the 5 fundamental numbers in mathematics in one simple, elegant, mysterious equation. Okay? What are these 5 ones? 0, 1, e, pi, and this is probably the most unexpected one, which is the not even real number, it's an imagined number, right? Now, see, people are still talking about this, no matter how many years, because people find this fascinating. Okay? So, what I accidentally discovered this formula also has 5 elements in it. So I was thinking about a way trying to make it sort of you can remember. Now, except that the mathematicians have taken away all the 5 important numbers, so I don't have these numbers to use. But I have, or statisticians have, symbols. So okay, so I'm going to ask you, what are the 5 most fundamental symbols or concepts in statistics? Especially because most of you raise hands, say you have taken a course in statistics. So I'm going to try on you. I already give you one. Mu. That's the average. Now you see, this was a lecture prepared for the general audience because I don't even use the typical E notation for expectation. I use average. Okay. There is a subtlety between E and average, but for this talk, I'm not going to get into that. So simply think about you have a finite population. Everything I talk about, the population is finite, and in real life, almost everything is finite, with particular type of population. So the average, or call it mean, is just, take an average, right? You know how to do that. Okay, what's the next one in statistics?
Variance.
Variance. Okay, very good. All right, so standard deviation, right? The square root of that, and the simple formula of that, except for this class, for this group, I don't have to explain that much, is the average of the square root deviation from the center, right? So that's, what's the next one?
Sample size.
Okay, very good. Sample size, you're slightly ahead.
Little n.
Little n, right, but there's a correlation. Correlation is a fundamental quantity that you should all remember. Correlation is what makes possible, particularly we're in a financial institute here, makes it possible to predict everything, right? Because there's something correlated. There's a co-movement allows us to predict. We're not getting to causation versus correlation. That's a philosophical talk. It's too hard, but at least you understand where the correlation comes from. Now, someone already mentioned next one is the sample size. That's obviously important. What's the last one? Population size, because I've already emphasized that. Although this is the one that most time people feel that's unexpected, right? Because you don't really, as I already mentioned, everything historically said, forget the capital N. Okay? But now I want to bring it back. Okay. So now I'm going to give you the formula. It looks like mysterious at the beginning, and I'm going to actually derive the formula for you. I know that's really very dangerous, but I will do it simply to tell you that there's no sleight of hand, there's no assumption made, because these results look so striking, but they are really because we have forgotten something very important. So here is what I would call the most beautiful statistical identity. Let's call it that way, right? So what it says is the following identity. It said, this is your sample mean. This is your estimator. This is your population mean, your estimand. The difference between them is an error. That's the actual error I want to study. Okay? And that actual error can be decomposed into 3 quantities. A correlation, a standard deviation, and a ratio of essentially how many people was not in your sample divided by how many people in your sample. Okay? So that error set, this term, this is the algebra. I'm going to show you in a minute how I derived that. But remember there are 3 quantities. A correlation, a standard deviation, and a ratio. Okay? Let me just go very quickly to you see this. Plausibly this may work. If you had everyone in the population, this part is 0, then this should be 0, right? If you had the entire sample, then it should be 0. At least this part looks right. And if you have no sample, the error should be infinity because you have nothing to estimate. Okay? So at least you see the extreme case looks right. But now I'm going to really derive this because this is the formula is going to tell us what's important and why we may have trouble. Okay. So now, let me actually reuse the 2016 election as an example to derive this formula. This is purely for this talk, because in the paper when I derive this formula, I don't need any specific content, but it's much easier to talk about this one. Okay. So let's say you did an election survey, and N here is number of people actually told you their preference. Okay? The number of people actually respond. And the N, capital N, is the number of eligible voters. Now, in real life, there's a lot of complication. People say they vote, they may not actually turn out vote. But conceptually, think about all the actual voters. Okay? What you want to study is at that moment, you say, I want to know that if election takes place at that moment, how many people will vote for, let's say, Donald Trump? Okay? That's the question you have. Now, here the thing I'm starting getting into a very important notation. Now, imagine that each of you, I'm going to convince that each of you actually, whether you like or not, each of you actually has a pair of random variable here. One is that, let's say you're the J's person, and if you plan for vote for Trump, we call you 1. If you plan not vote for Trump, I call it 0. Okay? So the 0 doesn't mean it's going to vote for Clinton or third party, or may not vote. I'm simply dichotomize everything. There is a much more complicated version which is not just dichotomy. The formula I show you does not require the binary, but it's much easier to talk about binary version. And that's enough. It's already causing quite a bit of problem. Okay? So each of you remember, you don't have to tell me whether you decide to vote for Trump or not, or whoever you want to vote for. But if you vote Trump, it will call it 1. If you don't, it will be 0. Okay? If you're undecided, it will be 0. Is that clear? But each of you will also have another random variable, which is the one that typically people don't pay attention to. And for those of us studying missing data, it's a key one. It's what we call the response indicator or missing data indicator. In this case, you say, if I ask you, say, who are you going to vote? If you decide to give me your answer, then the R to 1. Indicate that you actually give me an answer. If you refuse to give me an answer, it's a 0. Okay? So each of you also has this response indicator. Is that clear? But this is a key quantity. Okay? Now, I have to make an assumption that you respond honestly. But otherwise, the problem is far more complicated. If you tell me you vote for Trump, but you're actually thinking about somebody else, if you try to deliberately cheat, that's a different story. That's what we call response bias. That's even harder problem. But let's look at the simpler ones. That if you just whether you tell me or you don't tell me. Now you can see that each of you have an X and R. When I run through all these with you, I actually can do a simple correlation calculation. I can do the correlation between how correlated is X and R. And you can see where this thing comes. How correlated means like, if you decide to vote for Trump and you feel like, well, most people don't like Trump, so I'm not going to tell people, you refuse to answer, you see you start to create a negative correlation between X and R. If it was a random sample and everybody being selected by a random sample honestly give their answer, that correlation should be practically 0. Because whether you decide to answer or not has nothing to do with the value you're reporting. Is that clear? So the probability sample basically guarantee that correlation, at least on average, is 0. The self-controlled sample had this problem. That correlation may come out. Okay? So, now I'm going to show you how I get that formula. Now, the only trick I used, which is, again, for anyone who did this kind of missing data or sample calculation, finite population, it's a very trivial calculation, but it's a crucial one. This is the sample mean. The typical with sample mean, you look at all the people, right, in your sample, and you take their value, divide by n. Instead of doing that, I will write this thing as the entire population, but whoever is in my sample, this is a 1, it will be included. If somebody refuses to answer, this will be 0, it will automatically not included. Is that clear? I'm writing the sample mean in terms of population quantity using that indicator. Okay? Now why is that? Well, that basically, if you divide both numerator and denominator by capital N, essentially it's the average of this product and the average of the R. Average of R is essentially the fraction of how many people responded in the population. Okay? Now here is the magic. Once you write this way, now let's look at the difference. The difference between them, I already showed you, this is the ratio of average. And this guy is simply the average of all the x. The population mean is the average of all the x. Has nothing to do with r, right? So the difference between them is a ratio of the two average minus average. Okay? So what do? I take a common denominator, then the numerator becomes the average of a product minus a product of average. And that is a covariance. And any of you study correlation covariance, remember the correlation has two ways, covariance has two ways of writing it, right? That the product, the average of the product of the difference, or write it as the product of average minus the average of the product. Now since this is the covariance, if you standardize by the standard deviations, they become a correlation. But since I standardize by the correlations, I need to cancel that, so I put this one here, this one here. These two cancel with this, and this one with the original average of R. So why this is important? I'm decomposing into three quantities. This will be the correlation between R and X. It's going to tell me how correlated people's response behavior related to the value they want to respond. This is the sigma X. It's basically telling me the original X, how varied opinions of people's preference are in the population. And this quantity was an interesting one. The numerator is simply, denominator is simply the average of the R's, but this is standard deviation of R. Remember R is binary, 0, 1. For binary, you probably remember if the mean is P, the variance is what? P times 1 minus P. Okay? So if you put all these things together, these three quantities become the following. Okay? So now you see where the three quantity comes from. And I did this again. This is absolutely, there's no assumption whatsoever. All I did is algebraically re-express this side by this quantity. Why do I do that? Now I'm going to show you that when you look at this, say, well, this is what I want to study, but how? This tells you there's three reasons and only three. Yes?
I have maybe a slightly higher level question. So the canonical measure of interaction between variables, whether they're binary or whatever nature, is actually to look at a mutual entropy or mutual information. If we truncate a series expansion associated with the entropy function to second order only, we get this. My question is, why would we ever want to just truncate to second order?
Well, in this particular case, because all I'm looking at, and that would be great for the next level, in this case, because my estimator is a linear estimator. So all you need is just a correlation. You don't need the more, because that's because of linearity. But, when you estimate the population average.
If you assume deviations are second order, in other words, they are normally distributed by law of large numbers. So that's where law of large numbers comes in. Otherwise, you need higher order terms in the entropy expansion. Not just because of the mean, but you're relying on law of large numbers here.
Sure, but for this particular results, I'm doing finite probability calculation. I'm not even assuming X is random at all. There's no randomness going on because you could. I'm not even assuming R is random, right? Because the people may not change that. The X's are fixed, like whatever opinion you have, at least at that time moment, and R themselves. That's arguable. If it's a random sample, these R's could be random, depends on who gets in and out. But in general, if people self-report, you can imagine that no matter how many times you ask them, they either completely refuse to report or they always report. So these R's are, may or may not be even random. But my point here is that just look at this very simple case. This is just simple case. Take a simple sample mean versus the ones you want to estimate. This is in the simplest case. What you are mentioning is later, if I have non-random non-linear estimator, I may do these things to get this kind of effect. But this is the important point of this particular one is it's a complete generic. There's no assumption being made. I don't make any assumption about this being uniform or being a normal or being anything. I'm simply doing these algebra. Let me show you why this is important. So. What this says is because, as I said, because the sigma is P times minus P, here I use F, what you have is you're saying that the actual error, the difference between the sample mean and population mean, can be written in three quantity. The first one is what I call the data quality, and I'll tell you why. I already hinted at why I call it data quality, which is that correlation. The second quantity is really measuring data quantity, right? That's simply look at how many is not in the sample divided by how many is in your sample. So that purely is a measure of quantity, okay? And the last one is a familiar one that we all call, standard deviation. But if you think about, that's measuring the problem difficulty, right? If you're trying to sample a population, if everybody has the same opinion, just like I said before, it's an easy problem to solve. Just take one person. The more variability among the population, the harder the problem is. So what this equation tells you, that in order to reduce the errors, you have three, and only three ways of dealing with it. Increase your data quality by reduce the correlation. Increase the data quantity by increase little n. Or reduce your problem difficulties. So that's the intuitive way of thinking about it. Anytime we plot these problems, at least for this is a very neat one because I'm using that simple average. The data quality, data quantity, and problem difficulties. So in classical statistics, what we have been doing is the probabilistic sampling basically guarantee this guy to be as small as possible. In fact, the average of this will be 0. Okay? And I'm going to show you the calculation in a minute. Not only average is 0, it's a variance, or rather the mean square itself is going to be very tiny. And that's the important thing. Actually, probably from this you can see this guy had to be on the order of 1 over square root of capital N in order for these things to cancel, because this one is going to stay. The problem difficulty is not going to disappear. Depends on how many, regardless of how many samples. And you can see this quantity typically is going to be in classical statistic settings. This is going to be enormous. This is going to be huge, right? As I said, capital N is say 230 million, little n is say 5,000. This number is huge. The reason you can still get the reasonable error is you can imagine this correlation had to be incredibly small in order to cancel that. Okay? So this is now the statisticians like to look at the mean square error version, which is going to square both sides and take expectation with respect to R, and this is the one that it gets more. Okay, so now you can do this mean square error version, and again, I don't care how the design is, because this is generic. So again, now what I'm calling is this expectation of the row square. I call it the data defect index, because that's the quantity really trying to tell you how representative your sample is, or how much it can, how mixed well. Now, this is the interesting part. You can do a simple calculation. You can show that if it's a simple random sample, then the row, its mean is 0. Its variance equal to the expectation of square is given by 1 over capital N minus 1. So what that says is that correlation, which can cause problem, if it's truly probabilistic sample, that correlation itself is on the order of 1 over capital N. It's mean square. You see, this is the quantity saying the probabilistic sample does so well because it controls that correlation almost completely negligible, right? Because its mean is 0, and the variance itself is on the order of 1 over capital N, not 1 over little n. Little n is a sample size. It's that capital N. It really matters. In general, you can show that for any probabilistic sampling, it's actually a very simple argument that it has to be on, if it's a probabilistic sampling, it has to be on 1 over capital N. So the problem then is, this is a serious problem. The problem is that if this correlation stays away from 1 over capital N, then you can see no matter how tiny it is, it's going to multiply by the capital N. It's going to be large. Okay? So to convince you that I'm going to write another way, the actual error, which is I already showed you before here, divided by what I call the benchmark one, it's slightly technical. Essentially just that if you pretend a simple random sample, there is a benchmark one you can write down. But whatever it is it tells you that a relative error is the capital N minus 1. You can ignore the minus 1. It's just square root of capital N times the row hat. So what that says is that if you have a correlation, if people self-report creates that correlation, then if the correlation stays, then the larger population, the more error you're going to make. And the error rate goes up as a square root of capital N. It's very interesting because standard classical theory tells you the error rate goes down as 1 over square root little n. But this tells you that if you have a bias, if you hit a bias, the bias is going to magnify by the capital of the square there. Okay. So what is the impact of that? And there's also the mean square version. So here is the striking results coming now. What I can do is to demonstrate how bad this is. I'm going to do the following. I'm going to say, give me a data set. You know there's some defect. Let's say there's a number here. I'm going to say, I'm going to equip these arrows with a simple random sample with a sample size. I'm going to show you like how much sample size it takes for the simple random sample to reach the same error as your large data set, but with the data defect. Is that clear? The so-called effective sample size. So all you have to do is just to match these sides. Now the difficulty is exactly the same because I'm solving the same problem. So by solving this, I'm not going to go into detail, but I want to show you this is all rigorous because when I show you the results, you say, wow, how could this be? So you can check my slides as well if you want to, okay? So you can write down what's the effective sample size in terms of the data defect, and what's important is this quantity. Now, what this says is the effective sample size is controlled by, one is not by how many samples you have, but rather by the fraction in that population. So this is what the previous did a great question about, well, what's the population size? So now you can see, when we talk of big data, if there's a defect going on, you shouldn't just talk about the actual absolute size. You should look at the relative size. That's number one. Number two, there is this rho square here. Okay? Depends on the value of rho. Now here is the troublesome part. When you look at the formula, the only reason I use approximately because you can ignore this division n-1, and so that's not really relevant. But here is the striking part. This was actually a picture. Early I give this talk, one of the audience really liked it, so he actually made this plot to show how the effective sample size as a function of f. F is the percentage in your population, and the rho and which rho. And you can see these curves that if the rho is large, you essentially need almost 100% of the data in order to get anything effective. Now, but of course the 0.5, 0.01, this seems all very large. But what if rho is 0.05? Okay, so this is, let me tell you a story now. What I'm saying is, suppose the correlation is 5%. There's a 5% correlation. Now 5% correlation in many other studies seems very tiny, right? And also you cannot even publish your paper because the correlation is not strong enough, okay? But now let's say people have this tendency to not report when they want vote for Donald Trump. They decide not to report. And that tendency can be measured mathematically by a rho at 5%. If the rho is 5%, what that means is that if rho is 5%, 1 over rho squared is 400. What that means that if f equal to half, f equal to half, which you have 50% population, the effective sample size will be 400. So what that means that if the rho is 0.05, which seems very tiny, you have the opinions from half of the population. For the United States, let's say that's 160 million people. The answer you got statistically is equivalent to having a good quality simple random sample with 400 people. That is the type of striking results that people say, well, how could it be? 160 million versus 400, caused by that correlation equal to 5%. So a very natural question, and of course, this is essentially 100%, 99.975, loss of sample size. The question that people say, okay, Charlie, this is maybe way too big. Okay, the 5% correlation may be way too big, and it is too big. But I'm going to now show you using the data set from my wonderful colleague from 2016 survey to show you what was the correlation, at least for that survey, corresponding to for the 2016, and what kind of damage it can be caused. So here's the survey that done by my colleague. And anytime you do survey in real life, there's always complications. So you can see there's already at least 3 ways of doing it. What they did is they have these surveys before the 2016 November 8th that election. They go back really a few months. They do these follow-up. The raw sample is 64,000, and this is their prediction using the raw samples, just simply using the raw without doing any adjustment, and how they predict anything above 45 line, that's over predicting. Below is under predicting. On the line is predicting right. This is to predict how many vote Clinton is going to get. So you can see now, surprisingly, they over predict for the red state. Red state is the Republican state. They under predict for the blue state, which is the Democratic state, and the green states are the so-called swing states. Okay. The problem with using these data, these are the people pre-elections. You don't know actually who will actually go to vote, because you want the sample from actually the voting population. So what they did is they asked people, like, when they answer the question, do you intend to vote? If you say yes, or they ask you, like, there's some percentage you put down, they actually do this adjustment. Okay? So this is based on the adjusted sample, trying to match whether people vote or not. So, but you can see the sample size is smaller, but the general pattern, the numbers are a little bit different. The general pattern are still the same. But this is still not trustworthy, right? And these adjustments are actually very rough. So this last one, in some sense, is most trustworthy, although it's much smaller sample, is now they actually, in the United States, after you vote, because they know who they are, that you can actually go to validate whether you voted or not. So there's all the algorithms doing it. So it's not a perfect validation. It's itself has selection bias as well. But whatever it is, that in this case you will see, this is for Clinton. The striking part obviously is for this is for Donald Trump. No matter which way you do it, you see every state. These are different states. Every state you end up predict. This is what really happened. The only not even state, that's the Washington D.C. that they did not end up predict, because we know actually the actual voter was 93% for Clinton. So it's very hard to end up predicting for Donald Trump. So these are what they have. But what I was able to do is to do this. Remember how I write the difference equal to a correlation multiplied by this quantity? But now election is one of these situations that in the end you actually know the answer, right? So after the election, I actually know what the true answer is, and I know each state what's the prediction. So I can back calculate using that formula to calculate what the row was. Now I'm interested to estimate how much people were not lying but the end of reporting. So I can do that calculation for every state. And because it's a binary, I can also calculate sigma squared using the actual one. So this is just a formula to remind you that we can actually calculate the row after the election. And here's what happens after these 50 states, 51, because plus DC. You see for Clinton's row, they at least cover 0, right? The good ones should cover 0. The row should not be biased, okay, on average. So this is for Clinton using the raw data. And guess what happened? If you look at Trump, right? You see the Trump thing, the shape looks similar, but it's shifted. It has about 0.5% correlation, negative correlation. Not 5%. One digit down, 0.5. Okay? The 0.5, you see it because this is the DC. You see it does not touch 0. It actually has this bias. Okay? This is using the raw count, and I just should convince you this phenomenon exists regardless what you did. This is using that propensity adjusted count, and again to the same phenomena. For Clinton, it's sort of as predicted. It's sort of centered in the middle, but for Trump, it's a centered at minus over 5. Okay, and again using the validated sample, similar phenomena. Now all these numbers are a little bit different, but you got the picture that there's something about that Trump. The correlation is around the 0.5%, roughly 0.5%, minus 0.5%. Okay. Now you ask me how much damage does that minus 0.5% do? Let me give you this illustration. Actually, I look at all the surveys done before the election, and usually there will be like 20, 30, even 50 surveys published. Among a few months, if you put them all together, I did a rough calculation. It's about having about 1% of the eligible voting population, about 2.3 million people that their opinion is in this collective data. So that's about like 2,300 surveys, each with 1,000 responses. If you are a sort of poster or anyone doing these studies, that you might think that that's a lot of data. If I have like 2,300 surveys, and each has about 1,000 people, and if they all give me the same answer, I should be very sure I'm going to win, right? Okay. Well, let's do the calculation. Using that rho is 0.5%, right? Do the calculation, you will see the formula turns out to be about 404, and that is not a factorial sign. So this is a striking result. This kind of result saying, if you put all these surveys together, about 2.3 million opinions. Imagine yourself working for the Clinton Foundation or Clinton campaign. You say, well, that's a lot of sense, right? It's a very different story if I tell you that statistically I can show you, now retrospectively I can show you, the quality of the confidence that you should put in that answer is the same as I told you that there was a survey with 400 people, everybody answered honestly, a high quality survey, but only 400 people. I bet you will act differently. If you think about, that's all you have is 400 people. And I just show you mathematically, okay? Now I'm going to show you one more step to show you why this really matters. And there's also, and this is, everything is causing by that 0.5%. And why it's so bad, it's all because of this. See? This is what we call the sort of butterfly. I don't know if that's perfect effect, right? The rho is small. But don't forget that you multiply by the square root of n. So the way to understand this thing is imagine you want to aim the moon, and if you miss a tiny bit here, by the time you get the moon, you're going to miss really several lines. And that's the effect that's going on here. And it's the traditional statistical theory why it works, because that rho is exactly 1 over capital N. It cancels. If you have a perfect mixing, this number is way too big. This should be 1 over square root of n, as the mathematics show you. So, but what I'm arguing is this is a realistic correlation, and it's out of our control. It's people's self-reporting behavior. To really convince you this effect, let me show you this couple of last pictures, and I should really stop. You take the raw data, you do the usual plus minus 2 confidence interval, 95% interval, and because we now know the answer, we actually plot the answer. Okay? We plot the answer against the total number of voters from that state. This is for Clinton. Now, the plus minus 3 interval did not really work too well because we're using the raw counts. Okay, there's more fancy adjustment, so on and so forth. But I want to use the raw counts because I'm trying to detect people's behavior. Anytime you do adjustment, you're trying to adjust against that kind of behavior. What you see here is, for Clintons, you will see pretty much that some state cover, some state not cover, but you don't see a general trend. But this is for Clinton. Okay? I'm going to show you for Trump. Now, if you have been listening to my talk, you should be able to predict what the shape should look like. What shape should look like. Anybody want to guess? Well, I'm going to plot exactly. We have 50 state results against the standard plus minus 2 interval, 95% interval, and you should see a shape of this. What shape should we see? If you have been listening. What?
Sort of below and hooking down.
This is the actual result. This shows that if you just did the standard plus minus 2 interval, the predictions, the errors goes, the more voters you have, the further away, the larger the prediction errors. That's completely against our common wisdom. Common wisdom is all the small samples are the one that has more variation. Well, that's because that's a random noise. I'm talking about bias. The rho gives you bias. With the bias, the more people you have, the more cumulative effect it has. And that clearly shows. And if you look at it, these states really matter. Wisconsin, Michigan, they're all here. Now, what I'm hoping, what I call the 2020 vision is, I'm hoping that whoever is going to run next election, and hopefully we won't get into such a chaotic situation, pay attention to these large states. Because it is a large state, it's going to kill you. Because of that kind of bias. Bias doesn't go away just because you have more people. Bias gets confirmed when you have more and more people. If they all have the bias the same way. Okay? So this is really what I call the law of large population. And so another way to think about it, I'll be using this to scare people. The bigger the sure we fool ourselves, and this is literally the case. The only state we were able to cover is DC, not even a state, Hawaii, and Vermont. These are the tiny, tiny ones. The tiny ones, there's still a variance term, give you some protection. The larger ones, the variance, who cares? Variation is all, it's the bias stays. It's a mean square error with large sample. The variance is completely ignorable. That's why all people say, oh, with large data, we don't need to worry about statistics at all, because it's all ignorable. But yes, that's true. But you forgot there's a bias term. And the bias term is going to kill you. Right, so that's a, let me stop it here, saying, what are the lessons learned? What matters most is the quality, not the quantity. 2, don't ignore seemingly tiny probability data set when combining data source. I think this is probably a very important lesson. When you try to combine, in your study, you may have one set that has like 2 million people, the other has 200. You probably tend to say, oh, who cares about the 200? I have 2 million. Well, I just show you that 200 maybe is all your story. Okay? And so that's, you really should pay attention to that. Watch the relative size, not the absolute size. Always ask yourself, well, so how large was the population to start with? The question that we forgot to ask for a long time. Probability sampling is an extremely powerful tool to ensure data quality by making the correlation small, but it's not the only strategy, right? Because the whole game is, if you have a way to reduce that correlation, your probability sampling is a good way, but it's not always. Then the last is that we may all have too much confidence in big sets. I think the problem is when we see this zillion surveys, the data with these days saying, oh yeah, no, I mean, a tiny 0.5% correlation, who cares? Well, you should care. Otherwise, you may not get the president you want. And absolute last slides. I'm not an expert on election, but my twin brother, Andrew Gelman, and some of you probably know him. He writes a blog. He's a professor of both statistics and political science at Columbia, and he just wrote a paper on 19 things we want to learn in the 2016 election. All I'm talking about is just one of the problems. What do we learn here is, remember people talk about this shine chocolate effect. People means that people lying. Actually, the evidence here is not people lying. People just refuse to give the answer. Or they say, I have not decided. They don't purposely lie. There's not much evidence that they actually, they vote for Trump, they say they vote for Trump, they say they vote for Clinton. The answer they typically give is say, either say, I have not decided, or they refuse to give. And that is enough problem to causing that kind of correlation. So, thank you very much. Yes.
I have a quick question.
Yes.
I'm wondering if there is a relationship between the work that you've done, which looks at residual bias due to correlation, in effect in stochastic mini-batches across a large population, and the ways in which things like the Bonferroni correction try and avoid this. Superficially, the work feels a little bit like some of the thought experiments that led Bonferroni to Bonferroni corrections in classical statistics.
Well,
what do you think?
That's a great question. That I mean, everything I've done here is absolutely nothing new other than sort of writing down expressive formula in terms of the classical statistics about missing data mechanism, worry about all these R's. But I have not thought about the connection with the Bonferroni correction, because I have to think about that we can talk about. I'd be more interested in, because Bonferroni correction is more about these hypothesis testing situations, right?
Yes, but where you have correlation between the sample, the stochastic tests in mini batches, and you want to come out with an unbiased, but because of the residual correlation between the tests, your inference overall is entirely biased. And the Bonferroni correction corrects for the residual row, which is exactly as in your case. So superficially, the two feel
yes,
so
I can actually see that, because if it divide by some related to the size, cancels with the square.
And it also has the square root of n, escalation of bias.
Yeah, you're right. I can. Thank you. That is one connection I have not thought about. Yeah.
So let's think about let's think about most of us are indeed more familiar with statistics of imagining infinite population. So the way that I relate this is actually you're actually in pretty good shape, because if your finite population, you can actually, at least in theory, reach 100%, and then you are good. Okay. Now in the statistics in infinite population, this is basically like variance bias trade-off, right?
Yeah.
And rho is bias, right?
Yeah,
So we do learn, right, with infinite population. Basically, yes, when the sample size gets big, the variance gets small, right? But
Yeah.
bias doesn't change, right?
Doesn't change, it's
So
fixed.
basically, if you can do the same calculation, right? You will see the effective sample size will actually asymptote, right? Basically, if you get because all that you can get to is the variance becomes 0, right?
Yeah.
But the bias will always
It always
stay.
stay, yes.
So compared to a sample that more bias,
You get infinite. You get a zero effect.
yeah, basically, even if you have infinite sample, because your population is like even more infinite, right?
Right.
So you will still, even when you have
Absolutely.
infinite sample, you still correspond to a finite like sample, right?
Right.
So in your case, it's really paradise, right? Correspond to that, because that like you have no. Even if
Absolutely.
you get to like infinite sample size,
Yeah.
you're still screwed. Yeah.
No, that's absolutely right. But I would question that. I was just thinking about this. I would question that if you really go to infinite sample, first that's always the theoretical sort of construct. Is I'm not even quite sure if the correlation is the right measure, because it's much harder now introducing these R's.
Yes.
Yeah. So that's there's something more subtle there. But you're absolutely right. If you have a biased mechanism sitting there, you have infinite populations. It's never going to go away. The relative sample size probably is always 0, and is effective to what you can learn. Yeah. So, but that just reminds them is how vulnerable or assumption about all the stuff related to the assumption that we mix perfectly well. We made that was a great theory to make things work, right? But we need to recognize how vulnerable. Historically, we probably don't worry that much because the population, the data is not that large, or at least. But now it's everything just shows up because the huge population, in fact. So. Yes.
There was somebody else.
Okay. Go ahead.
Hello. Yeah, I think it was a great talk, very clear, very engaging. I wonder how much of that would translate to, let's say, multivariate setting, like a multivariate regression, where some of the covariates might be missing in samples in a way that is not entirely at random. Do you get similar effects there? Do you get similar scaling of effects?
Well,
there?
that's a great question. I mean, there's one thing I present in the most simple way, just text the x. In reality, you don't need just write the x. It could be a function of lots of variables, right? As long as the outcome is a scalar quantity, you can add as many variables as possible. And but it is much more complicated if those things are. If you now want to study some nonlinear fact, because everything is linear to make the story sort of looks as clean as possible. There's also a matrix version of it. Because, there's nothing to stop you to write everything in the covariance matrix. You can write those things. And really, I have not worked on those part. And what I wanted to do general, which is probably what Steve has suggested, if for these more general quantities, probably is not play with these formulas, but play with entropies, play with these informations. Got that kind of expansions to get that correlation. But the quantity. But I think I'm lucky in the sense of in this kind of province where there's a clear quantity to measure the data defect, and it's a one that most people understand. It's a simple correlation. That's given by the linearity of the problem. For more complicated problems, the real problem is to, other than the apparent data size, how do you find that one measure that it can to capture that data defect and potentially to estimate it. And so that, I'm hoping there'll be a lot more research out of this, but to just think about this whole concept of data defects. Yes?
So my question was, I guess, coming back to the entropy and so on. I should put my cards on the table.
Yeah.
My calling card says Steve Roberts Bayesian. The moment you start talking about bias and variance, I'm immediately wanting to say, hey, this all goes away if we do this in a Bayesian way. That is tantamount to dealing with information theory and dealing with this in an entropic framework. I don't think it goes away.
It won't go away.
But what it means, instead of having variance decreasing asymptotically but residual bias, it just means that we get bad Bayesian concentration parameters that are themselves biased. And those have a knock-on effect that the effective number of degrees of freedom in our data is massively reduced compared with the... So I think you still end up with the same answer, but it possibly has a few more extensions.
Absolutely.
We can put formally these are beta binomials over the votings, and we can do a whole load of stuff.
Exactly.
And I think it just generalizes this theory a little bit.
Yeah. No, you're absolutely correct. In a paper, I also mentioned like the histogram I learned from the 2016 naturally become apply for 2020 or make some modifications. Yeah. So basically, all I'm doing is I'm rewriting the bias we care about in terms of the correlation. Everything else is just it's a rewriting, but it gives you a measure, has a meaning you can think about, but also give you a measure is possibly more transferable from one study to another study, one election to another election, because it's trying to capture people's behavior.
Yeah.
So that's the thing. But you're absolutely right. And there's nothing. Essentially, if I put a prior on the row, is essentially I'm putting a prior on this a bias, potential bias. And there's absolutely you can do that.
So the a slight follow-up, if you were to do this over many elections, there is a lovely way called Bayesian classifier combination, where you treat each voter in effect as a weak decision maker. By weak, I don't mean mentally weak, but simply that they're an imperfect decision maker.
Yeah.
And
Yes.
if you know something about their track record, you have in effect an information correlation
Yep.
with other voters, and you can mitigate, as you combine all this, to remove the bias and the variance. And that is a very effective, and in terms of the principles of mathematics, we can't do better than that. So there's a lot of papers on that. There's possibly not enough data in this example, for people who are constantly providing weak decisions on a regular basis in things like crowdsourcing. These are incredibly effective ways of mitigating against the kind of bias, and it works very, very well.
Absolutely. We have a follow-up project. This data set I mentioned from my colleague, it actually goes back to 2005. So we do have the data over these years. So we're going to do this type of thing, just as you said, try to build.
I send you the papers and the code as well.
Please. Wow, even code.
Yeah.
And the
Here's
assistant?
another great colleague. Sending the paper, send the code. Send the data, send your assistant.
I haven't got any data.
That, yes, there are tons of things to be done. And again, I just want more people to pay attention to the issue of quality. Don't be just automatically assume, it's large enough, it's fine. Do this calculation. You might be surprised by what you see there. So, yes?
Professor Meng, there are two watchers here, both of whom requested Danny Kitishian and George Wong, whether you will make this presentation available because it's a bit hard to read over the live cast.
Absolutely. It's a $5 per person.
Okay.
It's entirely free, and as I said, that the paper is already online.
We can link to the paper online.
Yeah, paper. But for this, Cyrus or someone, feel free to email to anyone.
Or if maybe...
Post it, whatever you
Okay,
like.
we'll do that. Thank you.
Yeah. So that's absolutely no problem. Thank you all again for giving me a chance.